Hi, and welcome to my webinar today entitled Using RISA to Design a Building from Foundation to Roof. My name is Debbie Brisbane, and as Matt introduced me here, I will be going through the full building design here with our RISA system. So to jump right in here, let's talk about some of the things here we have in RISA, some of the software. The first three software packages here, RISAFloor, RISA3D, and RISAFoundation, is what we'll be focusing on. But some of you might be more familiar with RISA3D, which is our structural, general-purpose structural analysis software that can do any type of structure, 3 dimensions, does finite element analysis, and sort of your catch-all, does-all package. And RISA2D is listed underneath that one. We see that. It's very similar to RISA3D, just losing that 3rd dimension there. So you're just at 2 dimensions for that program. Some of you might not be as familiar with some of the other programs I have listed. RISAFoot is a spread footing program. I've got RISA Masonry, which does masonry wall design, columns, and lintels. I also have RISA Base listed here, which is a base plate program. RISA Section is a section properties program, and at the very bottom is RISA Tower, which does tower design for telecommunication towers and monopoles. If you have any more questions about those here, definitely feel free to contact us. But we'll be talking today about the top 3, which is RISAFloor to start with. RISAFloor is going to be a building-specific software. We're going to be designing buildings. We're going to lay out the floor by floor, and we'll be carrying loads down the building, designing all of the gravity members there, and then any of the members that are designated as lateral will be taken into RISA3D. In RISA3D, there's going to be some automatic load generation for us, so we can get the seismic and the wind loads generated and placed on that model and apply any of those loads there in RISA3D and design that lateral system there in RISA3D. When we're finished with that, we're going to take the entire model into RISAFoundation, so including all of the loads from the gravity design in RISAFloor, as well as the lateral design here in RISA3D. We'll go right into RISAFoundation and get a foundation design. Okay, that's going to be one model that we're going to be talking about, and they actually communicate all amongst those 3 programs. Okay, so if we start out here, let's talk about a little bit about the subjects we're going to cover today. So starting out here, we're going to do a total building design. That's the idea of today. We're going to start with how to lay out the building. There's a lot of different options, and I want to try to see and touch on some of the different options we have is to get the model started for the geometry. We're going to be talking about columns in particular, how they're laid out, and some of the different ways to view and understand how columns are loaded and actually the geometry of those columns in the program RISAFloor. We're also going to be talking about the loading, area loading in particular. One of the features of RISAFloor is that you have quick area loads, but we want to make sure that you understand how they are being applied. RISAFloor is going to be more of a design tool, so it's actually going to optimize all of our members. So we'll want to talk about the design criteria that go into that RISAFloor and see how we can actually alter our design to be the way we want it to be. A parent and child relationship allows us to optimize our multiple story buildings, and we'll be talking about that feature in RISAFloor. Diaphragms is the next topic, and that will be something we'll talk about. We have rigid versus flexible diaphragms available in RISAFloor and RISA3D. And then RISA3D, as I mentioned, does do lateral loads automatically for us, so we want to talk about how that works. And then we'll take the entire model into RISAFoundation. So starting out here, let's talk about the options for laying out the building geometry. First of all, you can start by drawing the model in RISAFloor. We can put, the first thing we'd want to lay out on that RISAFloor is put our supports in, and that's the way we kind of think about the columns and the walls as the supports underneath that floor plan. And as I mentioned, we're going to be working on a floor plan. Okay, we have a 3-dimensional model in RISAFloor, but we'll be seeing it as a floor plan. And then we'll be adding the beams on top of that system. Okay, so that's going to be our step mentality when we're using RISAFloor to start our model. The other options, if you have a complex model, you may want to import your model from a drawing. So if you spent some time drawing that up in AutoCAD, for example, or you're getting a model from an architect who's already spent time drawing that DXF file format, then you might want to actually start with that drawing, especially if it's complex. So well, we can save that file as a DXF file format. Any drawing can be saved as a DXF file format. And then what we'll do is we'll import that file plan by plan, floor by floor, okay, so plan level at a time. And we'll go through that process and see how that works. And lastly, you can import the model from Revit Structure. And one of the gains here is that you can import the entire model, okay, not floor by floor, not stick by stick, okay, but we're actually importing the entire model from RISAFloor, into RISAFloor from Revit Structure. And Revit Structure is a parametric model, so which means that all the information coming from Revit Structure, the material type, the members themselves, everything, even down to if it had a camber, things like that, are actually carried and maintained in the Revit Structure model. So it's a real intelligent way to do it. So there's a 3 steps here we're going to go through and see how to work with that. Okay, so I'm going to jump in and start doing that a little bit. So first I'm going to, kind of start here by, I'm going to actually jump into my RISAFloor program. So if you just find on RISAFloor, open that up. When we see here, RISAFloor is going to open up. And the first thing it's going to do is it's going to ask me, starting a new model. This is a little different than how RISA 3D opens up. It's a little, it's going to say, click here to create a new floor plan. Okay, because we're just going to start out, like I mentioned, floor by floor. So I click on that, and I want to tell the program a little bit of information about this floor. So I might give it a label, like maybe we'll call this basement. And the building that I have in mind here, I'm going to have it at elevation 15 feet. The building I have in mind here is going to be maybe a concrete first floor and then have 2 steel towers coming out of that first floor. Okay, so what I can do is I tell it for elevation of that floor plan, I tell it the default area load that I'll be using. So I have some defaults in here, but I'm going to just choose the first one there. Since the first floor is going to be a concrete slab, I can call that default deck slab, and that's fine. If I had a direction of that deck, I could tell it that right there. And I'm going to say OK. Now when you start your model in RISAFloor and you're doing it from scratch in here, the best way to do that is to set up a project grid. It's the easiest way. You don't need one to do that, but it's kind of the easiest way to get started. So the first thing is the horizontal grid. It's going to start at the z-axis, and I tell the program here 8 increments of 24, so 8 at 24 feet is what I tell it how many increments. I can do a start label. It's going to start at location 0, and I'm going to just click the generate button, and I see that 8 increments of 24 are created for us. We can add to this grid here just by putting and adding in things in, but what I'm going to do is just sort of modify a couple things by just typing a 10 on the increment. It'll override that increment there and recalculate the distance. And then put another 10 in there, and then I'm going to recalculate the distance. Okay, so I see things adjusted as I went and by clicking on that. And the x-axis, which is my vertical axis, I'm going to type in here the increments that I want. So I'm going to say 6 at 20, and that means 6 increments of 20 feet. And I say generate, and it will generate those increments of there for me. Okay, the next piece I'm going to do is also just edit these by just typing in a 15 on that one. As you see in the background, it just populates real quick for me. And I'm going to adjust this last one here to be maybe 15, and you can see it quickly adjusts. So if I close that down, now I see that my grid looks like that, what I have planned it to. And the first piece of information I'm going to start with is, like I mentioned, the supports. So you can start by clicking on the columns or the walls. And I'm going to click by starting with the walls. So if I click on the wall option here, I can draw in either masonry, wood, or general wall types. It's going to fill in the base to the first floor level that I have. So my first floor is my basement. And I'm going to tell it to be the material set concrete. The design rule we'll come back to. And I'm going to call this wall to be lateral wall. I can do a lateral or a gravity wall. Just so you know, that also make sure a lateral wall will get gravity loads as well. So whenever I say lateral, I mean both lateral and gravity loads, okay? So if I say apply, what I can do is sort of click on this grid intersection, and you see it sort of has a little red star there for me. And all I have to do is just click to another grid intersection, and it populates there for me, my wall. I'm going to do that a couple of walls around the building, and I just click a couple of times on those grid intersections, and I get some walls in place. Those walls are 3-dimensional, and the way I can kind of edit those walls and work with them is to double-click on them. I double-click on a wall. What I get here is my masonry wall. It says basement is where it goes from 0 to basement height. Okay, and then what I have here is just a rendered view of that. If I unclick on this rendered view, what I see is there's a grid behind the scenes. And what I can do is I can draw in any of these openings. I can create either door openings in this wall here. I can create window openings in this wall, anywhere along that grid intersection. I can also use the grid down below to help guide me if I needed to get to actually a specific location. When I draw that in, you'll notice that all of a sudden I do get a lintel automatically over top of that. So I'm seeing the lintel pop up. What I'm also going to do is I'm going to make sure that I click on the Draw New Regions automatically. What regions are, we can also call them piers of design. What they help us do is actually put the design in that area. Okay, so what we call a region would also sometimes be called a pier. And what I can do is I can double click on that region. I'm going to just put this over here for us. And what we see in this region, this tells us here all the design information for that region. So this is a masonry wall, and we're going to tell it either to be grouted, fully, partially, ungrouted, things like that. I can break out all the different pieces of the reinforcement, where to put the reinforcement for both in plane and out of plane. So this is an important note. You're going to want to make sure that you lay out your geometry, like your openings, and your reinforcement here in RISAFloor before we get to RISA 3D. It's just a good rule of thumb that all of the geometry and all of the information gets laid out here in RISAFloor, and then we'll take it to RISA 3D, even though the out of plane and the in plane, lateral design is going to be done later on in RISA 3D. So I'm going to say save and close, and it's going to be there. I'm going to say I can actually show it back again rendered if I wanted to, just by clicking on that little rendered button. Okay, and I can say okay, and I'm going to get out of that. The next piece I'm going to do is click on the columns. So we've laid out the walls. We can lay out the columns. This is going to be a concrete level. We have the option to do hot rolled, cold form, wood, concrete. Now, if you notice here on the right here, we can choose a material. I'm going to choose 4,000 normal weight. The thing is here, I'm going to choose rectangular as my shape group. In RISAFloor, we're actually calling out a shape group rather than calling out a specific column size. So rather saying 24 by 24 or 12 by 12 column, things like that, we say rectangular. And what that means is the program is going to go through and size that for me in a rectangular shape. Okay, I can tell it to be a function of lateral and gravity. Again, that means that it's going to get, if I called it lateral, it would get both gravity and lateral loads. But I'm just going to use these columns as gravity. So I say, okay, could do some rotations if I needed to. But I'm just going to say apply. And what I can do is just sort of click around these here. I can click on a grid intersection like that. I can box a grid to get those columns in there. So wherever I drag my mouse, I have a column pop up in the background. So I'm going to click around there. I also can just click right on the grid intersections like I showed you here. Okay, so I can click there and click there, click here and click here. I can draw these, a couple of these. And what my idea was that I have the two towers running above here in the steel. Okay, but my grid line 5 is kind of my dividing point for this these two towers above. Okay, but this concrete level is going to be sort of a podium design or a full design on the lower level. The next piece I'm going to do, this is a three-dimensional model, even though we are just dropping these in plan level. When I look at this one there, I can just drop this window down and I can show that it is a full model in 3 dimensions. That's important to note, okay? So when you're looking at it, we can go back to the basement level, okay, and you always can flip-flop between those. I did lose my graphical editing toolbar, and this happens a lot when you're flipping around there, but what you can do is just click on that pencil and it pops right back. And what I can do is I can grab these draw new beams to lay out my beam system. So I'm going to click on that. Again, you can do any of the different types of materials available. For us here, we're going to choose concrete. And you can also do a multi-material model. So like our model here, we're going to do concrete on the lower levels, and we're going to do steel on the upper levels. So I've got concrete. I'm going to say shape group is going to be rectangular. Okay, and these beams here are all going to be gravity, and I'm going to start them all as strong axis, and I'm just going to go and say apply. And what this does is here I can rubber band the entire building, lay out all those beams. Okay, the members here will just show here, the labels show me as rectangular. Okay, and then the last little pieces, I'm just going to draw in some of the pieces that didn't populate. And really what you're missing here is just the ones that go in between the walls. So I just kind of click around, and you can see all I'm doing is clicking right on that grid, and then the beams actually go into place there. Okay, so I'm going to just drop in some beams here. I don't have any infill beams, okay? Otherwise, I could draw some infill beams here using this repetitive infill beam framer. Okay, and this allows me to have specific spacings, and it'll actually do some repetitive framing in there. But my model is actually not going to have that. So the next piece here I'm going to do is after I've laid out all this, in order to enact some of my area loading, okay, I actually need to be able to have a slab edge. All right, right now we have beams and columns, but we don't have a way to tell the program where the extents of that slab or deck is actually going and where those loading would be applied to. So what we do is we click on this slab here, create slab. Okay, and I say create slab, and I can tell the program either to create it with an edge overhang distance of 12 inches, okay, or any edge overhang distance. I can tell it 6 inches. This is where the diaphragm is actually defined. So we tell it whether to use a rigid or flexible diaphragm. Okay, I'm going to tell the program to be using a rigid diaphragm on this level, and all I have to do is say create a slab and say consider all the beam edges, and just say apply, and it will go around the entire edge of the entire building and put in my slab edge there. So I'm all set, okay, on this level. And you can see here I've got my entire floor level started. All I would need to do now is start building another floor level. What I'm going to do sort of as a demonstration, instead of building another floor level manually, what I want to show you is doing the DXF import. So if I pop over to my AutoCAD drawing, this is a representation of my second level of my building. So we can see here I'm using actually wide flange in this level. W12 by 19s is mostly what I have on this here. And you can see if I zoom in a little bit, I've got my beams. My beams are defined here as just single sticks. I have layers actually called out. So right here you can see my beams are on a layer called beam lines. There's a little bit of standoff between the way it's drawn. So that's typical to the way a structural drawing is, where you have sort of a setback between where you're connected, so you can see that. What I also have on this model here is we click on one of those columns. I have a layer called out for my column. It's called column blocks. And this is actually a block, okay, so this is inserted as a block, and you can see the center point where that is inserted of my block. That's where the center point of that column is going to be dropped into RISAFloor. I also have all my grids in place. If I need, I actually have grids in where we're going to import it, but if we needed to import grids, we could. Okay, so all of this here is called is RBS Presentation Floor 2. So what I can do now is go back to my RISAFloor model, and I'm going to go to File, Import, and I'm going to import that DXF file. So I just click on Import DXF File, and I go up to my desktop. I'm going to find this file. It's right on my presentation folder, and it's called that RISAFloor RBS Floor 2. And what I can do in here is I can tell if there was a scale factor that was needed, if there was some unit changing that was happening here. The floor elevation here, you can set your floor elevation. I'm going to leave mine at 0 right now. You can adjust it in a second. My beam standoff, I can actually, so we said there's a little standoff between where the beam hits the girder typically, or each beam hits each other. If it's a column, there's a standoff, okay? On a structural drawing, you typically have a setback or a standoff. That's 12 inches on my model or less. And then you have to just put in here what your layers are that you called out. So my beams are on the beam lines layer. My columns here are on the column block layer. I don't have any walls, so I'm going to turn that off. And my grids are on the grid lines. Now ignore framing support for beam layer. You can turn that off here if you actually want it to not ignore that, but sometimes RISAFloor wants to frame things from beams connected to beams to columns, things like that. It's very important to what connects to what. So if you don't have things properly connected and uncheck that, it's going to sort of give you a warning message there. So I'm going to have it ignore framing supports, okay, and let it just go from there. I'm going to say okay. And all of a sudden here, I get my next floor all done for me. Okay, so it's right on top of the floor below. Just in case you didn't know that this feature here, we can see the floor below just by looking at our plot options, miscellaneous, show another floor. And I can show the floor below. So I can just make sure that let's see, show floor below. Let's see if I can see it. Maybe I don't, oh, okay, sorry. We are at the lowest post floor. I did that actually on purpose. We brought ourselves in at 0 feet. This is kind of an important fact, is if you forget to do your elevations correctly, you can just adjust them on the fly. Okay, so I now can set that up to be DXF floor is number 2, which is my second floor, not my basement floor. And I want to put it on 25 feet. I can adjust any of the names. This would actually be called first floor. And I can adjust that there. And what I'm going to do is close that. And now when I look at this model here, we can see that that floor level happens below it. And that's where the concrete beams are below it. And you can display that. Okay, so I'm going to turn that off. And we have this model here. So now we would sort of want to lay out our slab edge, right? If we wanted to go from here, and we can see the model, and we can look at it again in 3 dimensions and see how we could stack this model above from there. The next way I'm going to do this is I'm going to close this down, and I'm not going to save it at all. I'm going to bring it in using my Revit structure. So from Revit structure, if we look at this here, this is my model in Revit structure fully completed. It's going to be, just like we mentioned, 2 towers. Okay, we see here there's the concrete floors on the bottom, and if I zoom in a little bit, you can see my concrete columns in there. I've got some braces in here. Okay, on the left portion, the properties populate, telling me what size braces I have currently. At the top here, I've got columns running the full distance, so I have a large, tall column. And I zoom in a little bit closer, I can see here I've got joists at the very top of my model. Okay, so all of this work I've done, I've spent time building this Revit structure model, and then now I want to take this and share this model into RISAFloor. So what I can do is I can click on the Add-ins button, and you can download the Revit structure Revit link. Okay, so you have the link. I'm using 2011, the brand new link, and I can say Export to RISA. If you have this installed, you would see Add-ins, and then you would see Export to RISA. And in here what we've got is I've got the ability to look here, send it to RISAFloor or to RISA 3D, either one. Okay, we're going to send this to RISAFloor, which is sort of a natural fit for RISAFloor, this building type system. We can tell it to launch the program, which is what I'm going to do. If you don't have it on RISA on your system, you can send it to write it to a file and then send it to your colleague who does have RISA on their system. Okay, so I could actually export selected items only if I needed to. Maybe part of the building I want to send out to RISAFloor, but I'm going to send the entire model. The coordinate systems here, I can send it based on the project coordinates or the shared coordinates. It can send it oriented to north. These are some newer features we have in the new Revit structure link. If there was some sort of slack happening where things weren't meeting correctly, I could have some merge tolerance in there for the footings or for the actual whole model. Now this redesign members, what happens in Revit structure is you tell the program specifically what type of member you're using. And in RISAFloor, we're going to tell the program to use maybe a family, like we said, rectangular family for the beams and columns. And for the beams, maybe a family wide flange. And let RISAFloor design that, so based on what is needed. And that's what I'm going to tell the program to do instead of sending over specific things. I can tell the program to send over slabs. I don't have any slabs defined in this model here, so I'm going to keep that unchecked. And if I just say OK, it's going to run through. It runs through the model, creates all the RISAFloor joints and members for me, and launches my program. And I should see here on my computer, all of a sudden, it's going to create that model for me. Okay, this is done fast, really fast from into RISAFloor from Revit structure. We see that this is the roof level. Okay, well, let's check out our shapes here. We have our K-joists and our wide flanges on the exterior. I've got all my wide flange composite shapes below that. And if we look at our basement level here, we've got all of our concrete structure below that. So it's all automatically brought into you there for you. If you want more information on the Revit structure and how that link works, we just put on a webinar last week, and you can watch that. That's recorded on our website, and you can watch that webinar there. But I'm going to kind of jump forward here. There's a little bit of tweaking like putting slabs in, and so I'm going to jump to the one where I have already created all my slabs for myself here. I'm going to jump into that, and we're going to see here from the basement level, we've got this all started. I'm going to clear my results for a second, and let's just jump back in here and talk a little bit more about some of the things we've got in this model. Okay, so we talked here a little bit about some of these things when we were drawing them, but I want to talk about them in depth a little bit. Columns in particular are modeled in here as column stacks. And the way we define those column stacks is that they occupy a particular point in space. So that means that at a certain location in that model, we're going to see a column run We saw a lot of these columns run full height in our model here. But what we can see is that we can have columns that are single stack, story stacks, which means that they just run from one elevation to the, from 0 to 30 feet in this example. Okay, they just occupy one project grid, and they run from one lift. Okay, or lift is kind of a segment, is another way to say segment, and they go from 0 to 30 feet. With no splice in between. Or we can have multiple story stacks, which means that they run from 2 stacks. So they go from a same location, that same project grid, single project grid C2, but they actually live here from 0 to 13 feet, and then 13 feet to 30 feet, 2 segments, and you'll see 2 lifts. And this is an important concept here when you're adding splices into your columns. You can view the column stacks there with the column stack spreadsheet just before, but really a good way to see this is just by double-clicking on the column. You can see we have the column stack manager. And this really kind of flushes out what we were just looking at. So the column runs from 0 to 13, and then from 13.133 to 30 feet. 2 different lifts is what we call it, and we've got those listed there. You have the splice in the middle there, and the splice can either be viewed graphically like we see here, or we can look at the column spreadsheet, and each floor level that has that splice in it, so that we're looking at the second floor has a splice in it, we'll see in that column spreadsheet a splice checkbox. And that distance is that distance from that from that floor to the splice. So graphically probably is the easiest way I see it, and I can see using all of these tools on the left portion of this column stack manager, I can actually move or delete the splice and move it up and down, and that's a really good tool to use. So this is kind of a tool that a lot of folks don't know about when they use RISAFloor. Just double-click on your column, and you get that column stack manager. Columns are kind of something that we want to talk about, but also we want to talk about some of the design criteria we've got in this model. So like I mentioned before too, we're not calling out a specific member in RISAFloor. We're telling the members to be designed by RISAFloor. So we want to be able to manage that design using our design rules. And you'll find the design rules on the data entry toolbar listed under about 4 down here called design rules. And what it's going to do is it's going to allow you to be able to manage the maximum depth and minimum depth of the beams that you're doing, beams, columns. You can change maximum and minimum depth or the width of those maximum and minimums, and then maximum and minimum bending checks and shear checks. Now that's important to note, because a lot of times you'll have maybe a project that's your preliminary information. You don't have your full loading information on that project, and you may not want to design to the full maximum bending check or shear check. You may want to design to maybe 90%. So in here you put a 0.9 in there, okay? And then you would be able to have a little wiggle room when you finally get your loads actually finalized, and maybe they're a little higher, okay? So the next thing too, you also in a building design, it's very typical to be able to design your deflection and make sure that you're actually designing your members based on the deflection. A lot of times I'll notice that it's really not anything to do with the loads that are being controlled, it's the deflection. So we'll see here that we've got, we can actually define the deflection limit. So in inches based on the dead load, live load, or dead load plus live load, or the ratio itself, okay? So the dead load ratio, we can turn those into as well. And you also have the flexibility all the way on the right here to just change it based on any category, not just dead load and live load. Maybe snow load is something that you're really designing to, okay? And you can go there and change that category. The other piece here is our area loads. So we had, when we first defined that load, that floor, we put in an area load, and it was a default area load. And that was defined on the floor spreadsheet, okay, and we saw this floor spreadsheet when we opened that up and moved things around on that spreadsheet before. But what we can do on there is we can define an area load for the entire floor. Okay, that allows us to say that whole floor is going to either be publicly loaded, office loaded, roof loaded, and that just is a quick way to just put a load across a large area. That loading there is defined in our area load definition spreadsheet. Okay, and you can find that right on your data entry toolbar. And we have, these are just the defaults we have available, okay, office, storage, public, and piping. But you can add to this list, and I do recommend that you go in and modify this list to make it to what you need based on the type of materials and the type of building you're building. But let's talk about what these things are. So first of all, that additive checkbox. This one is an important checkbox because, first of all, what we do right now is that if you put a load on top of another load, they replace each other. Okay, so if I have a public loading on the entire floor and then certain areas I put some storage area there, it's actually going to replace that. The storage loading is going to replace the public loading. Now, if you want them to add to each other, so very typically a piping load is additive to another area, you would check this checkbox. Okay, so you can see piping is checked on there. And that would mean that one load will add to the other. Otherwise, just so you note too, whatever is the last loading is going to be on there is actually going to show you that. Okay, it's going to be the load that actually gets applied. The next option here is the pre-DL and the post-DL, and that's referring to our composite behavior. So that's pre-composite and post-composite dead loads. Okay, so we see here we only have some post-composites put into as the default. But if you want to do some pre-composites there, you might want to lay that out there. Live load types. Right now we have live load. We see here we've got some listed, and we've got live load when you can set it up to be reducible live load or non-reducible. You can also tell it to be a roof live load, reducible or non-reducible. If you're doing a snow load, you can put that in. You can do non-shedding snow load. You can also do rain load on that model. Okay, so you can do a lot of different things with the model there for the loading for your live loads, and maybe you would want to just specific things for if you're going to change it for a roof or however where you are in the model. Okay, the next piece you can do is a vibration live load. That here is going to be used to check the floor vibrations for the AIC Design Guide 11. Okay, so you're going to set up that right there. And the next piece here is the dynamic load, dyne load. Now this one's kind of confusing, and a lot of people get confused about what this is. I know I did before I used to work here. This is the dynamic mass, and this means that this is the load used for the seismic weight above and beyond the self-weight of the structure. Okay, which means that right now we are not putting in this pre-dead load and post-dead load. That's not being added into there for your seismic weight calculations. But what is this dynamic load. Okay, so you're going to tell the program specifically what you want in there for that dynamic. It's basically your superimposed load that you want in your dynamic or mass. Okay, a lot of times you have loads in those pre and post composite dead loads that are either conservatively large or inaccurately small, things like that, where they're not real loads that are happening for your seismic weight. So you want to separate these two and have this ability to control it directly. Okay, and you can see that dynamic loading there. When we talked about loading, we're actually talking about loading in one-way or two-way load attribution. And so you can define that. We're going to have it all here set up now currently. It's basically designed as a one-way slab here, or a one-way load distribution. We see that it's defined in the deck definition spreadsheet under the loads tab. Okay, so you can actually change that loads tab there and make it so that you want it if you want it to be two-way. And the picture below here just shows whether we have one-way or two-way load distribution. It kind of describes whether it's going to be loading it in one direction or in multiple two directions. Okay, and we can see that there. Let me jump here. There's one piece also I wanted to show you. If we're looking at that, that was in our deck definitions spreadsheet under our loads tab there. The other piece that is important to notice about the loads is that we do have our self-weight listed in here. And so this is the self-weight of the actual slab itself. And so if you do want to adjust your self-weight, it's listed in here. And if you did have any construction dead load or construction live load in here, you can list that in here. When I go back to the general tab, I've got some weight and I've got some thicknesses now, but this is actually where you're going to put the load on the slab is on that loads tab. These are just some of the default decks that we have available. You can always add to this list. Just type and enter here, listing, things like that. And if you do have kind of modify this, so this would be my test, deck, you might want to go ahead and actually modify these, and this is going to be very similar a lot of times, and click on the default button, which means that you save this to your default. So if you do spend time and set up a lot of stuff in here, you want to make sure that you are able to save those to your default so the next time you open the model, you have all those decks that you spent time working on. Okay, and you'll see this little D button at the top of my screen. The other thing about those self-weight loading, I just want to also make mention to this, is that if I click on my global parameters and I click on the seismic tab, the diaphragm mass self-weight option, okay, is going to actually be based on this lower portion, which is down here at the bottom. It says include the gravity items, include the deck, and then include the lateral items. And you can check things on and off, so you can actually use those things to help determine your mass properly, okay, which I'm also mentioning with that dyne mass. Okay, so you've got that all listed here. Let's jump back here for a second. The next piece I wanted to also mention was this parent and child relationships. This is a really, really great feature in RISAFloor that allows you to build multiple stories, common floors. Maybe a lot of times in buildings that I've worked on, you had maybe 2 through 10 were common, or typical is what the wording would be on a floor plan there. But what we really do in RISAFloor is we allow you to do this parent-child thing, where it says here the parent-child is the original floor, and then you can insert a child floor, which is a copy of the parent floor. And you can just do that by inserting a child floor. And you can see here on the floor spreadsheet what it does. It just says here parent is the first floor, and kind of in gray here. We can't really affect that, but it will let you see which is the actual parent of that. And what a parent does means that all the geometry and all the loads that happen on the parent floor will be populated and switched over to the child floor. That means any kind of changes you do on that parent floor, you're going to have affected on that child floor. But what happens also is that any changes that happen on the child floor do not get affected to the parent floor. So if you have special equipment, loading configurations on that child floor, they don't get populated back down to the parent. So it's a really good tool to use, especially on a big building. And then note, you can also detach the parent from the child. So it will just give you a big warning. There's no return. It won't let you go backwards, but you can detach them. So it does allow you to do that. Let's talk a little bit about the diaphragms that we did. We entered in the diaphragms. We defined it in RISAFloor when we added that slab and deck. And we had the option for rigid diaphragm, and we had an option for flexible diaphragm. In RISAFloor, we use membrane rigid diaphragm when we define a rigid diaphragm. The lateral loads are distributed in plane, okay, and we see that it allows the beams and the frames to take all the out-of-plane vertical loads. And that's what we're going to be defining when we have this rigid diaphragm in our model. We can see those rigid diaphragms and information more in the RISA 3D spreadsheet when we get into RISA 3D, and we're going to take this model into RISA 3D in a second. We can see that we can affect the eccentricity is here listed. It's for the accidental eccentricity for your seismic loads. Those are not going to be in your flexible diaphragm, but we can see that there. And we have here on the right side, it just tells us a list of whether it was a flexible or a rigid. Okay, and if you define it as a flexible diaphragm, which is a newer feature here, you can have your model use a flexible diaphragm in RISAFloor, and that means that in when we take it into RISA 3D, it's going to distribute the loads directly to the lateral members based on the tributary area there. And in RISAFloor and RISA 3D, when we take it over, it's going to analyze all the flexible diaphragms, so which means all the loads are going to be distributed to those just the lateral members, and that's an important note, and that's why I made that bold, is it only goes, all those members will go to the lateral members that we defined. So if you want the loads to be distributed to certain members, you need to make sure that they're called lateral. And in RISAFloor and in RISA 3D, we can design a wood flexible diaphragm. Okay, so in my example, I don't have any wood, but you can define a wood diaphragm. You just need to make sure you define a diaphragm region, which is using this icon right here that helps you define the region. And then the diaphragm regions need to be rectangular in shape, and they must be along the principal axis of X and Z. And then RISA 3D will provide you nailing patterns and panel thicknesses for that wood diaphragm, and it will give you the chord forces in there too. Okay, so that's for your flexible diaphragm. Let's see, we're going to take this, I'm going to jump back into RISAFloor for a little bit here just so we can get this. I'm going to run this model and take a quick look at the results. So when we've got this all laid out, this is from our Revit model, so it's the full model this time. We see this is our full RISAFloor model. Let's start on the top of floor. We can look at this. We're going to have a load combinations. If I click on that load combinations spreadsheet, I have all these different load combinations created. I'm going to solve this model, and it's going to run through all these different load combinations. And what it's going to do is carry all the loads down the building. We're optimizing every different beam and column. And I can see it runs down. I've got my beams, my columns. Everything's being designed as we go. And we can see it just takes a second or two. But what it allows you to do is go through the full design rules that we defined, and anything that we actually have it picking their sizes. And let's see here, 2 seconds. We're in the basement. And what we do here is now we're at the lower level. We can see here on the we're on our roof level, and I can always see that up here. I can also see on the bottom that I'm running what I'm displaying on my screen. So right now I'm just displaying here the loads if I had any loads to be shown, but all of mine are area loading. And what I can do is I can take a look at the results. So what we have here is it's 18K5. This is my joists that are being designed. If I zoom in a little bit here, I've got 18K5, and I can see all the different beams that are designed. These are non-composite steel beams that are going in here. If I click on the detail report, I can see one of these joists. Detail reports. The detail report is a really good way to kind of guide us through the program and see what's happening in each member. So if I click on the load combination, I can go and see the different load combinations that were created. This is our load that was actually applied to the beam. Scroll down, it's the shear forces with the moment and the deflection for that beam there. Now a joist has a special loading. It actually does the equivalent loading, so we can see it distributed to that load here, and we see the equivalent live load and the equivalent distributed dead load. And then it goes through the design there for the total joist, and we see the uniform dead and uniform live load that actually go in to create that joist design. Okay, and then we get a total reactions with the deflection criteria listed here. That's our joist design here. We can see that listed there. I'm going to go down to a composite floor, maybe of a 4th floor, and I can see that this is the composite design. When I have composite design, what I get in parentheses is my studs, and I can click on that detail report. I'm going to show this detail report here, and we're going to scroll down a little bit. We see the load that was applied, the shear force in the moment, the deflection, the axial forces if there were any. And what we see in here is that we get to see our shear forces, our shear capacity, and then it breaks it out into non-composite bending as well as composite bending. And I scroll down below that, I can see what percentage went into composite, and it tells me, and we always kind of see this, and I mentioned this earlier, but it looks like my deflection really is controlling most of the time. It's a way higher percentage for deflection versus any of the other things, so 97% deflection with the reactions and the vibrations are there too. So what I've got in here is we see those camber, we see the studs in there, and I also see some camber happening on the right side when I have a little C equal to 1.75 with my studs. And when I'm along this girders here, it actually breaks it into segments for my stud design. When I zoom out in here, let's take a look in our global parameters. The actual camber is controlled using my solution panel here. I can actually control the camber. So right now it's a minimum of 0.75, and it will tell me how much self-weight to be used for camber. Then I can also control my composite behavior. So I can use uniform studs only if that's what I want to be doing. If it's non-composite is optimum, that's what's currently happening, then it's going to go into non-composite behavior. Okay, and we control the different percentages of composite in here. So you can adjust all this information. I'm going to cancel out of there. The other piece I want to do also show you is it's important to note that you can actually design one of these beams in particular. I can click on the design button and then click on one of those members, and I can see why that 12 by 19 was selected. I can, first of all, if I push the optimize button, that is the most optimal beam. But one of the things is why was not another beam selected? So how come the 12 by 16 didn't work? And that one didn't work for several reasons. First of all, it couldn't fit the studs. Also, it looks like the deflection failed. Okay, and then we can even scroll down below that and say, hey, how come a 10 by 33 didn't work? Well, because it weighs a little bit more, right? So that's why it wasn't selected. But it does work. If I would rather use a 10 by 33, I could just say, okay, I get less studs, and I can see when I replace it, it uses the 10 by 33 now. So I can go around the building and make those selections, or over a large amount of beams, I can just force them to be certain things. okay, but it will allow you to help you guide you through that building. On the lower level, I can see which concrete beams were selected. Again, you get sort of a detail report is a really good spot to look at this and look through this here. Of course, you've got your different, this was a multi-span beam, so we're getting a little bit of a different thing happening here. Okay, and you get your code check information, and if I scroll all the way down at the bottom, I get a nice rebar layout here for my concrete beam. The other thing we always have here is our spreadsheet results. So you can take a quick look at your design results based on your what we're looking at. In the basement, we don't have any. So in the basement, we have concrete, all concrete. This is all based on material. Because this is a multi-material program, you always have to keep in mind that where to jump to. So in the basement, we have concrete, and we're seeing that. And then the upper levels here, we're going to jump over to hot roll, and we can see the design results based on that. Okay, studs, the maximum reactions. Okay. One of the newer features we added just out of a user request is that they said, hey, it's getting a little crowded in here and I can't see very well. So we have, if you turn your plot options on, you can turn off your show reactions and zoom in a little bit. Helps to guide you through in a little bit, and so you don't have to see all those reactions. But a lot of folks usually want to see that, so you can turn those back on. Okay, and like I mentioned also, you could double click on a column and see that different, if we had any slices in this. This was the column stack manager that we talked about earlier. Okay, so that's kind of all I want to really discuss in RISAFloor. We're done with our gravity design. There's a lot in here. There's a jam full of information here in RISAFloor. But what we're going to do is move into RISA 3D. And the way we do that is using our director button. Okay, I'm going to take that director and go to RISA 3D. And this is going to allow us to do our automatic load generation of wind. And it allows us here to pick from the wind codes we have available. So I'm going to choose the 05. You can choose the categories you want. It's going to probably always be 2 and above on that category, unless you're people are not in that. You're going to set your wind speed, your exposure category. You can set all that information up. And you see down below here, this is sort of an echo of what happened above. You can see all the factors that went into design. Below that, it gives us the KZs there, and gives us all the CP, the different width and length of that. And now we're seeing two things here. We're seeing a roof twice. We see 5th floor twice. And that's because we had 2 towers. So we actually have 2 independent diaphragms. And the way that this is being loaded is based on the diaphragm definition. So we see here on each side that roof that we have got 2 diaphragms, and then the basement was a 1 floor or slab diaphragm there defined. So we only have that 1 there. Okay, we're going to see that same thing happen here on the lower portion, and this is where the actual force is calculated. So 7.1 kips on that roof floor in the 1 diaphragm in the X direction, and 11.6 in the other direction. Okay, we'll see this graphically, so we don't have to really remember these right now, but just keep them in your head. We'll see it graphically. You'll always probably want to print this out for your record so you can kind of work from there. If I say okay, I can jump over to my seismic loads. The same thing happens in here. We're going to set up our parameters. We're going to set up our ASC 7 2005. We go in and put the CT factors in. The period will be calculated here, but we'll need an R factor, R value in there. And then per our location specifically, we're going to find out what the building code requires for our location, put our SD1, SDS, S1, and then we're going to put in our CTs there. And what we see once we calculate the loads, we can go below that and we see an echo of what happened above. But below that, it tells us the equation that was used. It tells us the period that was used and calculated. It tells us here the base shear for the building. And I scroll down below this, I get forces. Again, I see that same concept with each single diaphragm has its own force applied directly into it. And then below that here, I get pluses and minuses for basically adding our eccentricity that we'll see in a second. So if I say okay, I'm going to come out of here. The only thing that got transferred into this model is the lateral members. So only that was red there in the previous model is going to be carried in. And now that first it might make you nervous that you don't have enough of your loading in there, but you can see you have the dead loads and the live loads in here. And I'm going to zoom in a second here, and I can see that every place that a actual beam or joist framed into these members, I actually have the dead load, I have the live load. So it's all accounted for. All of that loading is actually accounted for, and there's no worry that you lost load. If you want to actually view the entire model, it's there for you. I'm going to just render this model, and we can see under Plot Options that I can go to Miscellaneous tab, and I can show the RISAFloor model gravity elements. And it's just for display, but they're there. Okay, it gets a little crazy, and this is kind of why you may sometimes not need all this. It's a really complicated model, and we just don't need it if we're just doing those lateral systems. So what I'm going to do is turn them off so you can see back again, kind of unclear that up. And what we've got now is we can see some of our our lateral loads. So I'm going to turn the loads back on, and I'm going to just drop down this list and see the first couple of things that are popping up here. So wind load in the X direction, we can see that we have wind loads applied to the model. And if I look here directly down on that model, or if I look here at the side of this model, I can see I have wind loads dropped in at each single floor level for each diaphragm. And let's see those diaphragms for a second, because we didn't see that. We actually have diaphragms listed out. Just like I said, you have two separate diaphragms. They're actually separate, acting separately. And so each one's going to get its own point load in there for the wind load in the X direction. We see wind load in the Z direction coming across. Let's turn those diaphragms off so it's a little clearer to see. Okay, and we can see here, we can see those different loading coming in there. You can also see in the earthquake in the X direction, so you have the X coming in there for the earthquake, as well as in the eccentric loads. So you can see that we have a little bit of eccentric on both sides. It helps us with that accidental eccentricity there. You get the on both sides there. And then we have all the different other loading. Now, it kind of gets a little complex when you're seeing all this different multiple stories, things like that, but you can pull it down by going to basic load cases. You can look at your basic load cases and look at this directly on the basic load cases spreadsheet by clicking on that joint load, and you see it kind of in gray here. So this is an easier way to pull it off and look at it, and you've got all that loading in there. What I'm going to do now is solve the model. So if I go to Data Entry Tool here, let's go open up our load combinations. I've got all these load combinations listed out, okay, and for time I sort of helped myself by picking the ones that were the worst cases here, and I use the load combination generator to get me here. So on that load combination generator, I can pick the code that was used. I can tell it to use eccentric or with quartering for both seismic and for wind. I get to choose those two options. I'm going to want to make sure that I always pick the X and Z at least if I'm using our load generators, okay, because they actually used our X and Z. That's kind of an important little piece here. We use the WLX, we use WLXZ, so we always want to use, when we're using our load combination generator, we always want to at least use our WLX and Z, and then we can also add the eccentricity ones if we need. Okay, so what I'm going to do now is solve the model. If I click on the Solve button, you can solve a single combination, you can solve an envelope solution, or a batch. I'm going to solve the envelope, and let's talk about what that means. The envelope solution is your worst case. It solves for basically your maximums and your minimums of everything, and that's all that gets saved. So we run through all the combinations possible, and then we do, as we say, save the max and min, forces, joint reactions, everything like that. Now the batch solution runs through all the same load combinations that I would do if I was using an envelope, but I save every single load combination's results. So it's a lot more information. Okay, so if you can see here, I'm just looking at maximums and minimums, okay? That would be the only thing that you're looking at. When I look at my design results, and that's kind of where I recommend you start, is always start with your envelope and then jump to your design results and take a look in here, because this is going to give us our maximums, minimums, and our worst cases, okay? So we're looking at the worst case code check of all the different load combinations possible, okay? And what we'll do here is I'm going to click on the code. I'm going to expand this out so you can see this code check. This is what our number that we're really concerned with. We want this 1 or below. And what I'm going to do is click on that whole column so it turns purple. And I'm going to say sort it, and sort it with the absolute max to the absolute min. So I want to see how bad it is. Well, I've got some pretty bad ones up here. Okay, I'm at over 300% on some of these different members. So I could start going through and identifying what the problems are, each one, okay? But what I want to do is more of a design. I want RISA 3D to design for me. So what I'm going to do is use the suggested shapes. So I'm going to close this, and I'm going to look on my results toolbar. After a solution is present, I get to have a suggested shapes. And what this does is it looks through the design list and says which shapes would be better suited. So some shapes are just too maxed out. They're not shape bound. But then some are not. Some are actually found for me. So what I'm going to do is I'm going to tell the program to rerun this entire model using every possible shape that it can use to either upsize some are actually might be downsized. In my model, probably not, okay, because I had so many failing. So I'm going to right-click. I'm going to say solve the model using the suggested shapes. And when I click on that, it says, are you sure? You've just requested for another solution. Basically, we're about to clear our solution. Do you really want to do that? And that's meaning that the whole model is going to get rerun. The whole stiffness matrix is cleared and rerun. And then sometimes some of these might change, and they are going to change, right? Because as the load gets distributed where some place got stiffer, load got brought into another place, okay, and dragged through that rigid diaphragm a little bit differently. So this is an iterative solution. So what we'll do is we'll solve this one time, and then we'll take a look at the results, and we'll see what's happening. And if you notice, I do have P delta turned on, so it's doing my shear P deltas behind the scenes, so it takes just a second longer. Okay, and then I see here that there's still some suggested shapes. So let's take a look at our design results. Okay, and I'm going to again right-click on there and say sort, absolute max to absolute min, and now I'm about 150% stressed. Okay, I can keep on going, and that's where I would want to keep doing. Keep working this until I get this down to a lower level. And then where I can't get it down to a lower level, I'm going to start examining. Maybe I need a stronger shape. Maybe a double angle that I'm using, the way I'm using it, is not going to be strong enough. Okay, so at this point, let's say I have about 27 members where I'm at that point. I need to start examining this model closer. So what would I do is I'd probably start looking at the plot options. Okay, and I'm going to look at the members, and I'll color code them. And I can actually color code them here with Unity Check labeled on there. Okay, so what I'm going to do is I'm going to say, all right, what is actually happening in this model? Let's take a look. Well, it looks like we're kind of failing. I'm going to turn the loads off here for a second, and we'll turn off some of these nodes. It looks like some of these braces are really failing. So we'd have to take a closer look at why this brace is failing. 125% on that one. Okay, and so I want to come in here and come closer to that one and what is actually happening at that point. The other thing I could do is with some of these things is to look at what load combination is starting to really have problems with. Okay, so this is just load combination 2. Let's just run that one and see when we run load combination 2 by itself, what happens in this model. When I solve a single combination, that's also going to be the best way to sort of debug or start design a little closer. Let's look at our design results now a little bit, see how many we're dealing with. Okay, so we're dealing with about 18 of them that are a little overstressed, and we can start looking at now one by one what's happening on this member. And I would then start looking at the detail report for one of these. Well, this one's not quite overstressed, but maybe that one is there. And why is this one being overstressed? And this one's not that large yet, so I maybe would start redesigning that. The other thing I would do is maybe take a look at the deflected shape. So I can click on the deflected shape, okay, and see what's happening on these members. Maybe they need to be tension-only braces or Euler buckling braces. Those give you options here to sort of help you with this model. Okay, the deflected shape is a really good way to say, hey, what's not working properly in our model? You'll notice here I had this new button. Okay, this is a deflected shape button, and I was able to put that on my model using my customizable toolbar, which is on my tools preferences. In my tools here, customized toolbar, I have a actual deflected toolbar button that allows me to do that. So once I have all these models, members in place, and all of my members are kind of going here, what I'm going to do is say well, we're going to have to work on this design way beyond this, but what I want to do is take this over to RISAFoundation. So I'm going to take this back. Actually, after a solution is present, that's all I need to do. I'm going to use my director button at the top of my screen and say RISAFoundation. And it's going to run into RISAFoundation. And I've already been here in RISAFoundation and laid some of this out because we are running a little bit out of time. But what I want to see here is that I have, in RISAFoundation, I can have grade beams, I can have slab definitions here, I can have footings, I can have any of those different situations in here. And I go to my global parameters here in RISAFoundation. And also, just so you notice, I have everything that came in from everything that came in from RISA 3D and RISAFloor came to RISAFoundation. So my dead loads They're all my column loads, as well as my my shear walls are coming in here as well. Okay, so my live loads. And now I'm going to find my earthquake in the X direction coming in here. I've got earthquake in the Z direction coming in here. Okay, the wind loads that we defined here, WLX and WLZ, all that is information here, and that's just from the RISA 3D model, but I have all of the other portions from the RISAFloor model coming in through here too. And you can turn the load description on here with the magnitude so you can see the magnitudes if you want on the screen. We also have a load category spreadsheet just like the basic load cases spreadsheet, and you can click on that and see the different loading that went into there for the earthquake load in the X direction or for the dead load, things like that. Now you'd place in your footings, and you'd place in your slab if you're coming in here from scratch using these tools here, draw a slab, okay, and you'll be able to draw in that slab just by telling it what thickness to use, and then you would tell the program here what footings to be using directly. Okay, I've done that already, so we don't need to lay that out. It's already finished. But what the other thing in the global parameters is I want to show you is that you've got in here, we can tell the program the entire RISAFoundation, the entire subgrade modulus for the model is 100 kips per foot cubed, or you've got allowable bearing, 5 kips per square foot, net allowable. If I have portions of the building that have different actual soil conditions, I can actually put in here and draw in a different modification of that. So I can say this portion will have not 100 subgrade modulus, something different. Maybe this section has 3 kips per square foot of allowable bearing pressure, and I can draw that in a portion of the model. Okay, we've got all that listed out in here. I'm going to turn those loads off. And the footing information and the design rules for that is all very similar to the way we define things in RISAFloor under design rules. So in here you tell the program specifically what you want to be doing here for the allowable maximum bending check, maximum shear check, the type of steel you want to be using, okay, the cover that would be in there for top and bottom. If it's the beams here, you're going to be telling it what the minimum bars are going to be for both flexural and the maximum there and shear bars. You can tell it exactly what you want, as well as the cover, the side covers for those beams. The slab definition, you're going to tell the slab here what the top and the bottom bars should be, number 5s to number 8s. So for the bottom there, you're going to tell it what the maximum top spacing is and the minimum spacing, and it's going to go from max to min. Okay, and then we tell it the increments we want to increment that spacing. And we can either tell it also just directly put the rebar in the mid-depth, not top and bottom, just mid-depth. Okay, for footings, you tell the program what type of reinforcement we want for footings. Okay, number 3s for top, number 4s for bottom is what I have. And then if I want to actually place pedestals on those slabs here, I can put a pedestal on that slab. All that information is defined in there. The footing definitions are defined in here too. Okay, so we can define those footings listed out here. And I can even change here some of whether I'm going to use overburden or a passive soil resistance here for sliding. Okay, and I can now, all of that information, I'm going to go to my load combinations here. Everything is placed in there, and the load combinations I get automatically put in here for, but I could go ahead and put more load combinations for myself using the load combination generator. I'm just going to solve with these 2 load combinations for speed here so we can take a look at some of these results. And as I solve the model, I run here through the solution. I can see that I'm running all the different combinations, the point loads, all that is being applied, and I'm doing an envelope solution. In RISAFoundation, it's always an envelope solution. Okay, so you get a spreadsheet here of the different point reactions. But what's nice in here is really kind of looking at the results graphically. For our slab, we can see here I have 8 number 8s at 18 on the bottom, number 5s at 18 on the top. In the horizontal direction, I see number 8s at 17 on the bottom in the vertical direction for that slab. And if I scroll down here, I kind of see very symmetrical results happening, very similar results, which is making sense for our model. Okay, and then for the footing design, if I click on the detail report, that's the one that I really like to look at here, because this footing design, it shows us a lot of information graphically. Okay, so we can see all the different information graphically on our screen. So we see here, first of all, we see the actual dimensions of that footing. It's a 6x9, 22 inches. It tells us the number of bars that went into that. Okay, so number 4 is what actually we're making up here at the bottom. What the pedestal is made up of, 20 number 3s. So maybe that's a lot of bars. Maybe we want to up those pedestals. We would go back and make those number 4 bars, so we maybe get less bars in there. We can see the geometry. Okay, again listed out. We see the loading that went into this member, or this actual footing here. Okay, we're just running the service load and we get a little soil bearing pressure. And we see below that we've got the footing flexure bars, the bottom bars, the footing shear check. We get punching shear listed out here. We see below that we have the pedestal bars listed telling us what the required steel was, the number of bars that were provided, okay, and the percentage of steel. If I scroll down, I get the bearing check, vertical loads only. When I do my overturning check, it's important to note that that's just your service loads, and we see that sliding is also just doing the service load. The service load was defined in our load combination, so we could control that, what becomes as part of the service loading. Okay, and we can see all of that there. We've got all those footing information. We have it listed out again here. You can take a quick look maybe at the pedestal design. Oops, sorry. You can look at some of the information on our spreadsheets. So if we were looking at point reactions, if we wanted to see the reactions here, soil pressures might be something that would be important for us to look at. What was the soil pressure and what was the allowable bearing? Okay, so we're pretty close to that line there. And if we had any beams defined, we would see that here. Okay, the other piece that's kind of cool to look at is our, if we zoom in and we can look at a detail report of a design strip. How did this design strip get designed? And so we see here the shear and the moment diagrams for that design strip. It gives us the code check information on that slab design strip. And then it tells us the cuts that actually went in here for the governing for this design strip. So X26 is a cut that went through here to design that. So if I look at the cuts, okay, I can see X26 shows us that in particular what design strip cut made that difference for that design strip. And I can flip through all the design cuts, okay, using the little arrow here. So this is a great tool to help us to actually get a design for this foundation. And we can use our director button here to jump back into RISA 3D. When we go into RISA 3D here, we get back to our original model. And then we see here, we have our lateral design in here. We're totally full with the results here. And I can go back into RISAFloor and take a look at RISAFloor. Now everything is being one model, okay? So when we look at this model here, we see everything that was happening in this model. It's all being updated as we go, okay? So we saw that we've got that whole, if we make changes to this, it's going to all trickle through all the different programs because that's one model. Let me jump back here. We talked about these lateral loads already when we were looking at it in RISA 3D. In RISAFoundation, just to note too is that those loads from RISAFloor, we said here we're seeing gravity loads as well as RISA 3D lateral loads. We're seeing both of those loads. If you're building a model just in RISA 3D and bringing that over to RISAFoundation, because those two programs also just interact together, you're going to make sure that you define your load categories, because that's what RISAFoundation is working off of, is those load categories. And then you can define your slabs and your footings and your grade beams in there. Final things to consider about the RISA building system. So one model for both gravity lateral design. That means that one file means less data to manage. All the changes that you make to geometry are going to be applied to the entire structure. It's a great tool to have one model and you're not having to actually make sure you make the change between different models. And I imported it from Revit Structure right there, but we can export your model once we're finished. So at this point, I can say File Export and send it to make it a construction drawing. I can send it out to a straight DXF file format. And just like we saw it when we saw floor by floor with the import, it's just similar to that where I can export it. And then also I can export it to Revit Structure. That same exact Revit Structure model that we just saw, we can update it with all the correct sizes that we had from before. Okay, so it's one round trip when you use a Revit Structure model. A DXF file format is not going to be a round trip, but Revit Structure is a round trip. So any changes that happen on either end, we can send it back and forth. We kind of went fast through RISAFoundation, but if you do want to learn more in-depth features about RISAFoundation, stay tuned. August 11th, we have a new webinar. Come visit our website, and you can check out the description and sign up for it. It's comprehensive design of shallow foundations with RISAFoundation, and Matt Brown will be talking about that one. Okay, so we've got, if you have any questions, let us know. Matt, I'll turn it over to you at this point. Thank you so much for your attention.